Optimizing generative models using static metrics can lead to a deceptive phenomenon called Fréchet hacking. While diffusion and flow matching models produce incredible images, post-training them to match real-world distributions is tricky. Researchers often use Fréchet distance loss based on static, pre-trained encoders to align generated and real images. However, directly optimizing these static targets leads to Fréchet hacking. The target metrics look perfect on paper, but the actual visual quality degrades, introducing strange high-frequency artifacts. Let's look at how this happens and how we can fix it. Static feature representations have blind spots that generators exploit to artificially lower distance metrics. Look at Figure 2 on page 4. When we optimize a generator solely using a static inception representation, it finds blind directions in the feature space. It injects high-frequency noise that technically reduces the inception FID score from 3.31 to 2.56, but clearly ruins the image quality for human eyes. Because the encoder is frozen, the generator learns to cheat the metric rather than improve actual image fidelity. Adversarial Fréchet distance, or AdvFD, solves this by adding a dynamic, trainable encoder that evolves alongside the generator. Instead of relying only on static, frozen encoders, AdvFD introduces a trainable representation branch. As shown in Figure 3 on page 5, this branch is optimized to actively find and expose the remaining differences between real and generated images. This sets up a dynamic, game-theoretic framework where the generator must constantly adapt to a moving target, preventing it from hacking any single static feature space. The training alternates between a generator update step and an adversarial representation update step. The core training loop consists of two alternating phases, the G step and the D step. In the G step, we freeze the representations and update the generator to minimize both the static and adaptive Fréchet discrepancies, pulling the generated distribution closer to the real one. In the D step, we freeze the generator and update the adversarial representation to maximize the discrepancy. This pushes the real and fake feature distributions apart, continuously exposing new mismatches. Real-Feature Whitening is essential to stabilize the adversarial training and prevent feature scale explosion. A major challenge in this setup is that a trainable encoder can easily cheat. It can maximize the Fréchet distance simply by blowing up its feature scales, leading to unstable training. To prevent this, AdvFD introduces Real-Feature Whitening. As shown on page 9, whitening normalizes the scale and covariance geometry of the adaptive feature space. Without whitening, the feature norms inflate exponentially and image quality collapses. With whitening, the optimization remains stable. AdvFD consistently improves visual quality and generalizes better to unseen evaluation metrics. Let's look at the quantitative results in Table 1 on page 10. Across multiple pixel space backbones like JIT and pixel mean flow, AdvFD consistently outperforms standard FD loss. For instance, on the GTL backbone, AdvFD reduces the FID score to 0.73 and improves the held-out FD, R3 metric, by over 41%. This means the improvements are not just confined to the training metrics, they actually generalize to entirely different, unseen feature encoders. While highly effective, AdvFD currently has limitations regarding scale, modality, and training computation. Currently, the evaluation is focused on class-conditional ImageNet generation at a 256 by 256 resolution. Its effectiveness on higher-resolution images, text-to-image generation, and video synthesis still needs to be validated. Additionally, training the adversarial encoder and computing the whitening transformation adds extra computational overhead during training, though it leaves the inference speed completely unaffected. In conclusion, adversarial Fréchet distance represents a significant step forward for generative model post-training. By replacing static targets with a calibrated, adaptive comparison space, it successfully mitigates the issue of metric hacking. This work opens up exciting possibilities for building more robust, high-fidelity visual generators across various domains, including video and multimodal synthesis. Thank you for watching, and see you in the next video.